Welcome to this video. My name is Chris Misa, and I'll present this joint project with Walter Willinger, Ram Rajan, and Reza Rajai, in which we'll try to convince you that there is more to internet invariance than meets the eye. So first, the internet is a moving, highly dynamic target. It sees continuous technological development. There's innovation and iteration in the protocols, applications, and services that underlie and depend on it. We illustrate this by looking at the number of RFCs published each year. Since the 90s, there have been over 100 RFCs each year. And so this is indicative of some interesting and continuous patterns of technological development in the technologies underlying the internet. There's also an economic angle to this, which is because the internet has enabled several new multi-billion dollar industries, such as cloud computing, broadband and mobile systems, AI more recently. These industries have each had profound and deep impacts on the evolution of the internet itself, how it is managed, how it is structured, and how it is organized. So to illustrate, we're showing here this tire tracks diagram of the evolution of a couple of these key industries. There's also a dynamic to the internet, which is this interplay and negotiation between organizations that manage finite resources required for internet operations. So internet IP addresses, AS numbers, different namespaces. To illustrate here, we're showing how the IPv4 address space has been shuffled around between different regional internet registries over time in this figure from Kano. So the inherent dynamics of the internet as a moving target lead to this sort of fundamental question of how can we ensure as internet and internet systems researchers that the results of our research retain long-term relevance. For example, if I propose a prototype system today, how can I know that next year there won't be some fundamental change in the politics, economics, or technologies of the internet that undermine all of my initial assumptions and hence require me to repeat all of my research effort? So we take advice from this paper over 20 years ago, referenced on the bottom of the screen here, which is that in order to address this concern, we should look for internet invariants. In other words, we should try to focus on what properties or aspects of the internet do not change over time, as all of these other aspects we've just alluded to do change. So what the heck does this actually mean? Internet invariants have typically been understood in terms of empirical evidence. So you think of some kind of distinct statistical phenomena, some type of distribution or pattern that you see not only in one edge case, but across all kinds of different internet-related scenarios. So different networks, different vantage points, different points in time, different applications, perhaps. In this project, we want to emphasize that there's another side to this concept of an internet invariant, which is to ask, what are the underlying design principles that might be causing or supporting the empirically observed statistical phenomena? And we contend that it's really critical for us to understand both directions of this arrow, essentially to have a connection between the empirical phenomena that we observe and the design principles that might be underlying them. This allows us to reason about how the current internet is operating, what matters essentially, how is it putting itself together. It also allows us to reason about future developments and advancements and proposals in terms of how they might impact the observed statistical phenomena. We'll focus in this talk in particular on what we're referring to as internet traffic invariance. So this focuses on just a particular single link in the internet, and we consider the structure of the traffic that flows through that link over a particular time window, for example, a day or an hour or something. So this traffic naturally breaks down into a temporal component. So how does the traffic properties themselves evolve over that time window that we've observed them for, as well as a spatial aspect, which is how is the traffic itself arranged in the different address spaces in that time window of observation. First, looking at the temporal structure. So study of the temporal structure of internet traffic goes back over 30 years at this point to the initial observation that these time series tend to have self-similar scaling. So this means, like we're showing in the figure, that if you look at the number of packets, for example, per time window, and then you zoom in to look at different granularities of that time series, essentially you don't see fundamental changes in the types of statistical behavior. So there's, of course, different spikes, but there's still a kind of rough spikiness to all of these, even though they're looking at, different granularities across orders of magnitude. The key thing that this raises, though, is why do we see this kind of behavior? What are the mechanisms that potentially are creating this? This was addressed a couple years later by a couple of works. The one we're looking at here establishes this idea that when you look at an aggregate time series of internet traffic, it's actually created by a large number of independent flows. And the packets from all of these flows get interleaved. But if you look at the flows themselves, they actually have a much simpler structure with these clear on periods and clear off periods. And so this leads to this on-off burst process model of internet traffic. And the mathematical results that were established at the time showed that if these bursts have heavy-tailed on and off distributions, then the resulting aggregate time series down on the bottom here will have self-similar scaling. This gives us a mechanism for why do we see self-similar scaling? Well, it's because the flows, the bursts have heavy-tailed sizes. The next question, of course, well, why do we have heavy-tailed sizes in the flows and bursts on the internet? So the initial attempt at addressing this is, again, a couple of years after that previous paper, and it essentially looked at the internet modeling these sizes in terms of highly optimized tolerance, this hot model. And so they considered a simple problem of web layout. So imagine you have some web content here shown by this string of rectangles, and the users want to access this content, and there's some different probability for each user to access different rectangles. And what you want to do is you want to break this content into a series of web pages that are linked together in such a way that you minimize the total transfer of content across all users while maximizing the ability of users to find the content they want. And the really interesting result that comes out of this is that essentially by assuming a couple of high-level design principles in this model, you can show that no matter the distribution of probabilities across this content, you almost always end up with heavy-tailed sizes of web pages. In other words, these chunks down here have heavy-tailed distributions. Of course, since each of these web pages has to be transferred through the network, through the link that we're monitoring as flows or as bursts, this is potentially an explanation for why we see that heavy-tailed property in the flow and burst sizes. So we get a link here back to the design principle, which says that why do we see self-similar scaling? Well, it's because of this higher level principle that the internet is transmitting information for human consumption, and the organization of this information essentially requires heavy-tailed flow sizes. Next, we'll look at the spatial structure. So this also goes back over 20 years. And the initial observations in terms of IP addresses arrangement in the address space when you observe actual traffic is that they have this highly cluster within a cluster structure that's indicative of what's called multifractal scaling. So to illustrate, we show here Hilbert curve projections of the IP address space. On the left-hand side, this is the entire global space. Each of these squares represents the IP address prefix. The color of the square represents how many distinct addresses are located in that prefix. This is a way to visualize the spatial structure of addresses. Of course, the blue regions are empty, the red regions are full. And what you can see here from the figure is that when you choose a particular cluster here and you zoom in on it, you see that that cluster is made up of more subclusters. And this repeats several times as you zoom into /24, where it becomes essentially too sparse to see any kind of clustering. This also holds if you look at different clusters of the space, and if you look at different traces, different observations. So it's essentially an observation of empirically verified invariant. Of course, the question becomes, why do we see this kind of clustering? So at the time, there was an initial proposal that it might have something to do with a mathematical model known as a conservative cascade. So the mapping here is essentially to think of addresses being some kind of abstract mass that gets split down the prefix tree according to some random distribution, which we call W here. And it's been known in the mathematics community that conservative cascades, under certain assumptions, if the distribution has high enough variance, they do produce multifractal scaling in the resulting limit sets. However, it's not clear how that connected exactly to multifractal scaling. So this leads us to the present day. All of these pieces we've talked about previously have been established, although we believe that there is some valid utility to the way we're organizing and linking them together in this presentation. However, what appears when we write out the table and start thinking about this spatial row is that there's several unknown open table cells here. And so in the rest of this talk, we'll provide some initial ideas about what could go in each of these cells. So first off, when we started thinking about the relationship between the conservative cascade model and the observed multifractal scaling of addresses in internet traffic traversing a particular link, we realized that under normal conditions, the addresses that we observe must have first been assigned, first routed, and even before that, they must have been allocated to some particular organization. So this led us to look at the allocation process itself as embodying the conservative cascade. And this is not a very hard jump to make. I mean, it's pretty well known, established this figure that allocation of address space goes through a hierarchy. There's the global organization INA that splits up essentially /8s to these regional organizations. Then there's local organizations and ISPs that eventually allocate to customers where the addresses are finally assigned, routed, and then observed in our internet traffic. The key thing that's missing here, however, that's a little bit subtle, is that conservative cascades are not inherently multifractal. They don't inherently produce multifractals. We have to also establish that there is some non-trivial variance on that distribution W. And so in order to do this, we looked at the present day allocation structure in the internet by looking at INA records, RIR records, and some other data sources. And we found that at least for the cases that we looked at, the records themselves have heavy-tailed allocation sizes. So across all of the RERs at this level, we see the same kind of heavy-tailed allocation size distribution. Of course, the node depth is the log of allocation size. Added levels also you can think of as the log of that. So this provides us a clear link finally between why do we see multifractal scaling in observed IP addresses? Well, it's because those addresses come from an allocation structure that is a conservative cascade with non-trivial variance of the cascade generator. So the next question that emerges, of course, is why would address allocations end up having heavy-tailed allocation sizes? It seems a little bit counterintuitive, like not optimal, right? So we try to approach this using the same ideas as in the temporal prior work, which is to come up with some highly optimized tolerance model that simplifies that process and allows us to analytically, and in this case empirically, through simulation, ask a whole bunch of what-if questions. So our simplified model assumes that clients request addresses directly from an upstream, essentially one level of a hierarchy, and that the upstream must respond to each client request until their address space is full. So then the key source of uncertainty here is essentially that the upstreams don't know how many addresses will be requested from a client when they see that client's requests. So the first time a client requests a single address, that client might only request one address or it might request 1,000 addresses. The upstream has to make some allocation decision for that client without knowing how many addresses it will end up using. We think this somehow captures the inherent uncertainty of the allocation process of internet addresses in general, outside of the current present day internet. The other constraint is that we have to minimize fragmentation. So for different routing purposes, it's commonly understood that you want to keep addresses from the same client in similar prefixes, in similar regions of the address space. So the interesting thing is that with this simple model, we explored a bunch of different scenarios, changing utilization, changing the different distributions of how many addresses each client actually ends up requesting. And in all cases, we observed a similar kind of heavy-tailed allocation size distribution as we see in the real-world present-day internet. So shown on the right here, there's this long tail, this heavy tail in the allocation sizes. So this leads us to think that the current internet has heavy-tailed allocation sizes, not because of some historical flukes, but because that is the result of these inherent policies or objectives embedded in this kind of hot-based formalization of the allocation problem. So finally, this connects to these different policies, in particular, the idea of maximizing utilization and avoiding fragmentation. And unlike in the temporal case, we realize these are actually explicitly stated policies of the various RIRs. So if you look at policy from Aaron in this case, they state explicitly that ISPs should essentially maximize utilization of their given space. They should try to minimize fragmentation of their given space. And so we hypothesize, although this is stated maybe at some levels, we hypothesize that these are policies that might permeate through all of the levels of that hierarchy, and hence underline the reason why we see heavy-tailed allocation sizes, hence provide a basis for why we see multifractal scaling in observed IP addresses. We refer you to our paper for many more details on all of these. We also want to reemphasize that we do not mean to establish our current solutions as the definitive answer to each point in this table. We hope, on the contrary, that by exposing and by linking these ideas together, we can stimulate and lead to future research on each of these points individually that strengthen our understanding of the spatial and temporal structure of observed internet traffic. Skip these questions. And with that, thank you so much for watching. Please join us on Discord for further discussion. Feel free to visit our project page and reach out to me if you have questions directly at the email address listed here.